This section is an introduction to vectors, and vectors are used to represent quantities that have a magnitude and a direction, such as you could be driving north at 50 miles per hour, so your magnitude is 50 and your direction is north. A lot of things don't have a magnitude and direction, such as, say, temperature. Temperature may be 72 degrees in a room, but there's no direction associated with it. Now, for a vector, the way we can represent them visually is by using what are called directed line segments. And so what we see is we have this directed line segment here. It's got an arrow indicating its direction. So I've got 1, 2, 3, 4. I've got 5 vectors. And the magnitude is the length of the vector. So the longer it is, the bigger the magnitude. And the direction is just the direction it's going. And if you can pick up a vector and move it, and as long as you don't change its magnitude and direction, that is its length or which direction it's pointing, it doesn't really change. So these two blue ones, for instance, they're parallel, so the same direction, going both up to the right, and also to the same length approximately, the way I've drawn it. So that means these are equivalent vectors. So here's some examples of how to find vectors and what we can do with them and how it relates to trigonometry. If we start from an initial point and go to a terminal point, go from one place to another, that is, the tail of a vector to its head, then we can look at it this way. If we have an initial point of 2, 5, so we start here, then we go down to 4, -6. So I go from 2, 5 to 4, -6, initial point to terminal point. I can take this same vector and move it over to the origin, just pick it up and move it so it's got the same direction and same length, and write it in what's called component form, which has these triangular brackets. And to get component form, you simply subtract the components. So 4 minus 2, that is terminal minus initial, is 2. -6 minus 5 is -11. And you can see that this is at 2, -11. So component form is based upon going from the origin and use triangular brackets. Here's another example. Point to point, going from -1, -3 to 5, 2. So the black one is the original vector. Component form will be here in blue. You can subtract or just think about the fact that going from -1 to 5 means you must have gone to the right 6. -3 to 2 means you went up 5. So 6, 5, or excuse me, 6, 5 is your vector. So you can also say 5 minus -1 or 2 minus -3, do it the subtraction way. So now that's where the trigonometry comes in. Let's suppose we have the components, say 6, 5 for instance, and we want to get the magnitude and direction. So here's an example of how that would work. The components are 3, -4. So that's the blue vector here. And you want to get the magnitude and the direction. And the magnitude is the length of the blue vector, and the direction is going to be related to this angle theta. And we've got north, south, east, and west. So what you do is draw some axes. You always draw axes, and draw your vector from the origin, since it's a component form, and then draw a vertical line back to the x-axis to make a right triangle. That's a key point in this. So draw this back to make a right triangle. Now, I know this is at point at 3, -4, so this distance must be 3, this distance must be 4. And now I can use the Pythagorean theorem to get this length. So I discovered that the magnitude is going to be 5. And then if I want to get this angle, 4 is an opposite and 3 is an adjacent, and therefore that'll be tangent. So tangent of theta is 4 over 3. So to get theta, I've got to do the inverse tangent, which is 53 degrees. So now I know this angle is 53 degrees. Now I can represent the direction a couple different ways. You can say the magnitude is 5, and we're going 53 degrees south of east. And what this means is start out going east, but then turn 53 degrees towards the south. Or what you could do is, instead of saying 53 here, I know that since it's 90 in each quadrant, this must be 37. So you could say, again, magnitude of 5, but 37 degrees east of south. That means start out going south, but then turn 37 degrees to the east. So there you go, you get your direction. So let's look at another example of components to magnitude and direction. Here my components are -1, 4. So you draw in the vector, label the sides, the legs of this triangle. After you make a triangle, of course, you've got to draw down a vertical. Always draw the vertical up or down, wherever the case may be, to the x-axis. So that's 1, that's 4. So to get the magnitude, I use the Pythagorean theorem. My magnitude is rad 17. So that's the length of my vector. To get my direction, I need to find this angle theta. Opposite over adjacent is tangent. So tan theta is 4 over 1. Use inverse tangent to get theta, and it's about 76 degrees. So my magnitude is rad 17, and I start out going west, but then I turn towards the north. So Rad 17, 76 degrees north of west. So it's a little confusing because the letters are reversed of what you're sort of physically doing. You start at west and then go 76 degrees north. So 76 degrees north of where west would be. Now let's look at it the opposite way. We're going to have a magnitude and direction, and we'll get the components. So this time, the magnitude is 6 kilometers. The direction is 30 degrees north of east. So we don't know how long 6 is, so just draw any length you want, but you have to make it an angle of 30 degrees to the north of east. So you start out going east, then turn 30 degrees to the north. Again, we draw down to get the triangle. The components are going to be given by the x and the y values of this triangle. And so we can use trigonometry to get those. This is an adjacent, this is a hypotenuse, so that's cosine. Multiply 6 to the other side, and you get about 5.2. Compared to this angle, y is an opposite, 6 is a hypotenuse, so that'll be sine. Multiply 6 to the other side, that comes out to 3. And so therefore, in component form, this vector, 6 kilometers, 30 degrees north of east, is actually 5.2 kilometers, 3 kilometers. So this is component form. Gets a little trickier in other quadrants. Here we have 10 miles southwest. And so southwest implies it's exactly halfway between south and west. So we know that this is 45 degrees and this distance is 10. And so rather than use trigonometry this time, let's just rely on the fact that this is a 45, 45, 90 right triangle. And to go from a long side to a short side, you divide by rad 2. So this is 10 over rad 2, and this is 10 over rad 2. But you have to remember, we're in the third quadrant, so actually this is left 10 over rad 2, down 10 over rad 2, so they're both negative. So negative 10 over rad 2, negative 10 over rad 2, which you can simplify to about negative 7.07, comma negative 7.07, and of course our units are miles again. Last thing is about adding vectors. First I'll show you how they add graphically. The way you add vectors is what's called head to tail. So if you want to add the blue vector and the green vector, we basically pick up one of them, it doesn't matter which one, and we move it so that the tail of the blue one will move to the head of the green one. So I pick up the blue one, and I try to draw same direction, so parallel, and same length. So basically, it's if I were to connect this up, I'd have a parallelogram, and then your overall sum, which is called the resultant, is from the very first spot to the end. So the red vector is going to be green plus blue. And I can show that a little more dynamically. Here I've got vector A, vector B, and then the sum is this one in blue. And you see if I were to take the red one and basically move it over to here, it would match up. So I'd go green to red, and then I just go from the start to the very finish. If they're going in opposite directions, of course, then the vector sum is nothing. If they're exactly on top of each other, same direction, just twice as long. So that's adding vectors graphically. Adding them algebraically, pretty simple too. You simply add by component. So if we have these three vectors, 2, 3, which is in blue, negative 4, 1, which is here, vector v in red, and vector w, 0, negative 2 in green. If I want to get u plus v, I do 2 plus negative 4. To get negative 2, I do 3 plus 1 to get 4. So that's going to be u plus v plus w, 2, negative 4, and 0, and 3, 1, and negative 2. And I get that is my result for u plus v plus w. And if you added them doing head to tail, hopefully you would get something that looks about like that. So let's say I were to just do u plus v. So I'll take my blue one and I'll put it over here. So let's see, right up to about there. And so then the overall resultant was this one, and that looks like I'm left 2 and up 4, so minus 2, 4.